Second option is to teach you some other thing like perpendicular magnetic recording or something like that. Okay, so what do you prefer? Going through all these questions, revise. So, when I started discussing the growth of magnetic recording, I told you that scaling was one way in which growth is achieved. So, we have been scaling down the grain diameter, we have been scaling down the thickness, okay, and making the bits smaller in length, narrower in width and so on. Okay. So, this leads to the problem that the grains are now smaller in volume. So, when the grain becomes smaller and smaller in volume, the KUV becomes lower and lower. Okay, KUV, the energy that retains the magnetization in a particular direction becomes lower and lower. So, you will notice that when the volume is bigger, the magnetization is stable as a function of time, but as the volume gets smaller and smaller, the fluctuation frequency becomes more and more. Okay. So, you can see 8 nanometer flips more rapidly than 8.5 nanometer cube of cobalt. Okay. So, this problem is called thermal stability, and so even if you do not apply any magnetic field, the remnant magnetization might decay as a function of time. So, in this measurement, even when there is no magnetic field, you can see that the magnetization decays as a function of time, because of the competition between two energies, which are the anisotropy energy and thermal energy. Okay. Then this was explained by Neil Arrhenius decay. So, where they said the decay of magnetization is based on a time constant, which is an exponential function of the ratio of KUV and KBT. Okay. So, if KUV by KBT is large, tau will be large. If tau is large, decay will be less, but if KUV by KBT is small, tau is small. When tau is small, denominator is small. So, this will be a large number, negative number. So, the decay will be significant. Okay. So, this results in the observation of a super paramagnetism. Okay. So, when you make particles larger, the particles will retain the magnetization in certain time for, in a certain direction for long periods of time. So, suppose I had magnetized all these grains pointing up, you observe after 10 years also they will be in this direction for 10 years, for example. So, if KUV by KBT is more than 60, so this retention will be for about 10 years. Okay. On the other hand, if I make the particle small, let us say I initially magnetize along this direction, but after I remove the magnetic field, so some of them would be in other direction. So, you observe these particles, they will be keep fluctuating as a function of time, like the animation that I showed you. So, because of that reason, these materials do not have a hysteresis. Okay. Superparamagnetic materials do not have a coercivity, but they do have a large magnetization, because these are still ferromagnetic particles. Within these particles, the spins are still parallel to each other. Okay. Do you think superparamagnetic particles have no use? Does anyone think that superparamagnetic particles have no use? Can you suggest some use for superparamagnetic particles?
They are used in biomedical applications.
Which application exactly?
Drug delivery or something.
Pardon?
Drug delivery or something.
Drug delivery.
Nanoparticles, superparamagnetic nanoparticles.
Okay. You are almost 90% right. Okay. These superparamagnetic particles are used, potentially useful in some application called magnetic hyperthermia. Okay, hyperthermia means let us say your body cell temperature is increased beyond certain temperature, right. For example, if the temperature is more than 42 degrees Celsius or 44 degrees Celsius, the cells will, if it let us say 50 degrees Celsius to be safe, let us say if the temperature of your body cells are at some high temperature, the cells will die. Okay. So, at slightly high temperature, cells will die, that is called the hyperthermia. So, this magnetic hyperthermia is a treatment people are looking at. Okay, let me break this here. So, magnetic hyperthermia is a treatment people are considering to get cure cancer. Okay. So, if you compare the temperature at which the cells die, okay, let us say the normal cells die at around 50 degrees Celsius, the cancer cells die at a slightly lower temperature of around 42 degrees Celsius, for example. Okay. So, there is a difference at which different cells die. So, normal cells can tolerate slightly much higher temperature compared to, these numbers you do not take for granted, I am giving some rough numbers. Okay. Cancer cells die slightly at lower temperature. Okay. So, if this is the case, let us say at some place there is cancer. So, let us say you inject some particles here. Okay. So, these are magnetic nanoparticles. Okay. So, you inject magnetic nanoparticles and magnetize them up and down. Okay. So, you let the particles undergo through lots of hysteresis loop. Okay. So, you magnetize them, demagnetize them, magnetize them, demagnetize them, do this for like this this hysteresis loop is carried out in several hundreds of kilohertz. Okay. So, you are doing this operation at very high frequency. Okay. That means, even within 1 second there are so many hysteresis loop traced. Okay. You know that the area under this curve is the energy spent. Okay. So, if you have a hysteresis loop, you go through one loop, that means basically you have spent some energy. Okay. So, when you inject nanoparticle and you let them undergo so many hysteresis loop, basically energy spent. So, this energy will result in rise in temperature. Okay. So, by controlling the time and the number of nanoparticles that you have, you can reach at this temperature, for example. Okay. So, if your body temperature is 38 or whatsoever 36 degree. So, from 36 degree Celsius you go to 42 degree Celsius by carrying out a hysteresis loop of these magnetic nanoparticles. Okay. So, this is how you raise the temperature of the cancer cells to 42 degree Celsius and you can kill the cancer cells. Okay. So, this treatment is called magnetic hyperthermia. Okay. So, here I am saying that the super paramagnetic particles are useful. Okay. So, do you find any contradiction in whatever I am saying? First of all, I said super paramagnetic materials have no hysteresis loop. Okay. They have saturation magnetization, but they have no hysteresis loop. And here I said if you have hysteresis loop, then there is some energy, that energy is the one that gives rise to this temperature increase. So, I am contradicting, right. So, what is the difference? How the super paramagnetic materials are useful? Yeah, nano. So, you can send them easily through the veins and things like that. So, that is one thing, but there will be no big difference between say 8 nanometer super paramagnetic particle versus say 20 nanometer non super paramagnetic particle. There will be no difference in sending them to your body, that is not the difference. Okay. So, first of all, why super paramagnetic particles are useful? If you ask why super paramagnetic particles are useful, so to answer this question, let us assume that the particles are not super paramagnetic. Okay, if the particles are not super paramagnetic, so they will have certain, these are all single domain particles. So, they will have certain magnetization direction. Okay. Okay. So, when they are not super paramagnetic, they will have a fixed magnetization direction. So, when you put them together, they will agglomerate in such a way that, I mean, the north south poles, they will get sticking, they will start getting sticking and so on. Okay. So, when they are not superparamagnetic, the particles will get agglomerated. Okay, so, they have a remnant magnetization, that means when they are not superparamagnetic, they will have a remnant magnetization. Remnant magnetization is not 0, that means they have north pole, south pole. So, they will all get closer to each other, like two magnets stick to each other. So, all these particles will get agglomerated. Okay. So, if that is the case, we cannot use, suppose you make many number of particles, right, they will all agglomerate together, then it is difficult to inject these particles into the cancer cells. Okay. So, what you want is, you want to have a fluid. So, in this fluid you want these superparamagnetic nanoparticles to be isolated from each other. So, you do not want them to get attracted. Okay. So, for this reason we want superparamagnetic particles, because superparamagnetic particles have 0 magnetization, that means they have no fixed north pole south pole. So, they will not get agglomerated. Okay. So, for this reason superparamagnetic particles are desired for magnetic hypothermia. And now, let us come to the second point. So, I told you that superparamagnetic materials have no hysteresis loop, coercivity is 0, but I said the energy product of, I mean, the energy spent is coming from hysteresis loop. So, there should be some coercivity, right. So, these two are contradicting with each other. So, why or how I am right in saying that we can use superparamagnetic particles? Okay. So, when you have a superparamagnetic particle, we are talking about a time dependent everything, time dependent magnetization, which depends on this, right. So, if you remember, I told you we are doing this at hundreds of kilohertz. So, when we measure hysteresis loop of superparamagnetic particle, what is the time scale we are talking about? Okay. So, time scale is like, maybe we hold the data for, I mean, we hold a magnetic field for say maybe 5 seconds or 10 seconds, something like that. So, we are talking about few seconds of time scale in which the hysteresis loop is measured. So, we will not see any coercivity for superparamagnetic particle. So, if you keep a collection of superparamagnetic particles in some fluid, you observe the fluid, you are going to talk about some long time scales longer than seconds. So, whether we keep the superparamagnetic particles stored or we measure the hysteresis loop of superparamagnetic particles using a VSM, we are talking about few seconds. But when we do hyperthermia, we are magnetizing and demagnetizing the superparamagnetic particles at hundreds of kilohertz. Okay. So, kilohertz is milliseconds. So, hundreds of kilohertz will be, we are talking about 10 microsecond kind of time scale. Okay. So, there are some equations people have derived based on this formula. We can actually derive an equation for coercivity as a function of time. Okay. So, if there is small KUV by KBT, coercivity also will be a function of time. So, it will be some H naught plus something which is actually a function of time. Okay. I do not remember the exact numbers here, but there will be something here which says that the coercivity will be function of time, and that will give you a time dependent coercivity which will look something like this. Okay. So, at longer time scales the coercivity is small, low coercivity, but if you go towards smaller time scales, the coercivity will go higher and higher. Okay. So, this depends on KUV by KBT. Okay. Let us say KUV by KBT is, let us say this is 0, then let us say this is something like 10 kilovolt. Okay. So, the time dependent coercivity will look like this. So, in this graph, out of these 4 graphs, which one represents large KUV by KBT? Which color represents the largest KUV by KBT? Green. Okay. So, this, I mean, when KUV by KBT is very large, suppose it is even much larger, it will be something like this. Okay. Coercivity will be almost independent of time if KUV by KBT is very large. Okay. So, for intermediate KUV by KBT, you will be here. So, if KUV by KBT is very small, you are here. If it is too small, then you will reach even this point, that the coercivity becomes 0. Okay. So, let us say this is seconds, this is kiloseconds, sorry, milliseconds, let us say this is microseconds, nanoseconds, and so on. Okay. So, we are choosing some particles either here or here. Okay, but if you are doing operation at microseconds range, these particles will have some coercivity. Okay. So, when you do the hyperthermia, the superparamagnetic materials will have hysteresis loop like this. So, either at a small time scale, you will see this, or at low temperature you will see this. So, superparamagnetic materials may show a hysteresis loop at low temperature or at small temperature, small time scale. Okay, let me erase this one, this is going to confuse you. Okay, so, at small scales superparamagnetic materials will still have a hysteresis loop and they have a coercivity. So, you are using this energy to raise the temperature of cancer cells and kill cancer. So, when you store them, we are talking about some time scale like this where they have no coercivity. So, when you have stored them in the solution, their magnetization is fluctuating as a function of time without any magnetic field. But when you go here, you apply magnetic field, they respond to the direction of your applied field. Okay. So, this is one application of superparamagnetism. Any other questions here? But in hard disk technology, superparamagnetism is a problem in two aspects. First aspect is that you will lose your data, okay, because you are storing. So, let us say you have a coercivity as a function of time looks like this. Let us say this is say a few seconds. Here we are talking about years. Here we are talking about say a few nanoseconds. Time and coercivity. So, when you do VSM, you will observe this kind of coercivity. Okay. But if you extrapolate for 10 years, they have very low coercivity. Because of this reason, they cannot retain the information for a long period of time. Okay, that is one problem. Okay, retention is the problem. Another problem you see is here. Okay. So, when we write data in hard disk drive, we are writing data so fast that like you write one bit like this, another bit like this, another one like this. So, you keep writing data. So, this writing time scale is around 10 nanoseconds. Okay. So, if you have a time dependent coercivity which looks like this, what happens is when you are writing information, the recording media has a very large coercivity. Okay. So, that means your writability is going to be difficult. So, these are two implications of superparamagnetism. So, it is a problem in hard disk drives, but it is useful in concepts like magnetic hyperthermia. Okay. So, in hard disk, if you are making the grains smaller and smaller, you will have the problem of data loss. Okay. So, this we have seen before. If you make the grains smaller and smaller in volume, then your data is not stored for many years. Ideally, once you magnetize, they should be like retaining the pink and blue, but if the grains are too small, some pink will become blue, blue will become pink. Okay, blue and pink represent north and south poles, for example. Okay, if you make them smaller and smaller, the data is not retained. So, you cannot read 1 or 0. Here you can say this is 1, this is 0, but here and they have reached this kind of small volume, they do not retain the 1s and 0s perfectly. Here you cannot make out 1 or 0. Okay. So, this is the problem. Let us skip questions. So, when we keep scaling, we encounter the thermal stability problem. Then I also told that the technology progresses by making many technological jumps. Okay. So, we look for jump from one technology to a totally different technology. Okay. For example, when the hard disk drive was made in 1956, the magnetic recording media were made from magnetic particles dispersed onto some substrate. Okay. So, how they made the hard disk media is based on this paint. Okay. So, this is basically a paint. So, it has some solvent and magnetic particles are dissolved in that solution. Okay. Basically, it is a solution embedded with iron oxide particles. Okay. You know how they made the particles uniform? They filter using a SOX kind of thing. They filter all the particles, then they pour this paint onto a spinning disc. That is how they coated the magnetic recording media, the first magnetic recording media. So, this was the kind of technology for many years until 1980s, then where they switched to the thin film media. So, okay. The sputtering comes into picture only in 1980s. Okay. So, making the jump from particle based media to sputtered thin film media is one kind of technological jump. Okay. It is not easy. Okay. It involves a lot of risk for company. So, hard disk media moved from this spin coating to sputtering. Also, as I mentioned, the head was basically a coil manually wound, and they used the same coil for reading and so on. But now nowadays we are using machines like this to sputter the hard disk drives. So, the hard disk drive equipment, the disk media manufacturing equipment has around 20 plus chambers. Okay. So, these are like modular machines. So, for example, let us say you have module 1, 2. So, you can have until n, then you will have n plus 1, n plus 2 all the way to 2n here. Okay. So, if you want 20 chambers, this n will be 10. If you want to 22, there will be another 2 and so on. So, you can keep adding more modules. So, you can keep increasing the number of chambers if you want. Okay. Suppose the layers required for magnetic recording getting more and more, you just add more module. Okay. So, if you make n is equal to 13, you will have 26 chambers. Okay. So, people can increase the chambers if they want, and so here we are loading all the disk in class 10 clean room. So, I told you what is a class 10, right. It means you have, let us say 1 cubic meter. Within that 1 cubic meter, you will find only 10 particles. Okay. So, in this room, for example, you may be able to spot 10,000 to 100,000. Okay. This room, but in the class 10 clean room, this number of particles is just 10. So, that is the kind of clean room where they load the disk and so on. And this whole operation is completely automated, no human touches anything. Okay. So, the loading, unloading, everything is automated, no humans involved. So, the disks are clean. So, why we do such clean operation? Why not have a few particles here and there? Okay, so, in hard disk, as I mentioned, we have a disk that is rotating, then we have a head that flies over the hard disk, okay, and reads or write information. Okay, so, this you learned. Do you know what is the spacing between the disk and the head that flies over the disk? What is the spacing? This spacing used to be micrometers in the past, okay, but currently this spacing is 1 nanometer. So, the spacing between the head and the disk is 1 nanometer. So, if the spacing is 1 nanometer, if you have one particle which is even say few hundred nanometer, and particles are typically micrometer, right. So, they will cause crash. It is like you are trying to land a plane, but there is a rock in your runway. Okay. So, there will be crash, then the hard disk will be spoiled. So, they want to minimize all this contamination. Okay. That is why we operate in the class 10 clean room, and we make the disk everything clean. So, if you are going into the area where this sputtering is going to happen, right. So, in companies you have to like fully cover up. So, your head, everything is covered up except your eyes and your gloves, and in some companies even after you wear the gloves, you are supposed to wash your gloves in the tap, only then you can go. And this gloves will be like you are wearing a suit, and this gloves will be like hold tight by something. Okay. So, you are fully covered. So, if you go in, you are not going to contaminate the clean room. Okay. That is something. Then usually most clean rooms, right, they do not allow people with say makeup. Okay. So, if you are working in the clean room, you are not supposed to wear makeup, because you will be generating some organic contaminant. They can spoil the performance of the things that we do. Okay. So, technologies like hard disk, MRAM, these are all very highly sophisticated technology. And here I also want to say something about discipline. Few years ago, right, I mean these days people can buy a lot of electronic things in India, but a few years ago people tried to get say TV or whatsoever from foreign countries, and when they bring something, let us say we bring a Sony product to India. Okay, Sony has many factories. For example, there may be a Sony factory in Japan, they may have Sony factory in Philippines or China, something like that. Okay. Many companies, I mean many countries where the same company may make product, but people will still prefer the products made in Japan. So, I used to wonder why it is the same company. So, there should be same quality in the products that Sony makes. So, why distinguish between something made in Japan or Philippines? I used to wonder, but later at some point of time I realized that there is some difference between the countries in which some product get manufactured. That is from this aspect. Okay. So, to give you some anecdote, I went to some factory in some European country. Okay, I won't name the country, but some country in Europe. So, you will still associate some discipline with Europe, right. But in that company they were making hard disk drives like this. So, you are supposed to maintain everything, you are supposed to be gloved, and everything has to be completely protected. When we went to that factory, the guy who is working in that company, he got a phone call and he picked up the phone from his pocket and started talking. Okay. This is completely not allowed when you are talking about operation like this. Your phone, you cannot take it out. Everything is supposed to be clean, and your phone is outside, its phone is contaminated material. And if you use the phone in a clean room, then let us say you are making some batch of hard disks. So, those batch is going to be spoiled. Okay. So, because he flipped the phone out, so there will be some thousands of disk which would have contaminated. Okay. So, the disk drives, those which use this disk, right, they would be like spoiled, I think. They may get spoiled over a period of time. Okay. So, this brings us to this concept of discipline. So, if this happens in Japan, I mean it will never happen in Japan. Okay. Japan is so disciplined, the Japanese people are so disciplined, they won't do this. Okay. Even they may not even carry the phone inside the clean room, but if you lack discipline, this might happen. Okay. So, the product you make will be different, even if it is Sony, right, depending on the discipline of people, we may have poor product or good product. Okay. So, this is very important. So, you are all going to be researchers, and you may, some of you may work in the industry. So, please follow the protocols. Okay. Whether you are doing research or even driving or riding bike, follow the rules. Okay. Now, let us come back to science again. Okay. So, there have been lot of technological jumps like this. So, particulate media to thin film media. Then if you take head, we learnt about inductive heads, magnetoresistive heads, GMR, TMR and so on. Okay. So, these are the technological jumps through which we move towards high density. Okay. So, in that sense, let us come to the second topic, which is called the perpendicular recording media topic. So far I have been mostly talking about the longitudinal magnetic recording technology, where the magnetization of the disc media is parallel to the disc surface. Okay. On the other hand, perpendicular recording media has two differences. One difference is that the magnetization is lying out of plane. So, your north south poles are up or down. Okay. So, this is one difference between longitudinal recording media and another the perpendicular recording technology. Secondly, you will also see that there is a second magnetic layer. Okay. So, we have one ferromagnetic layer which stores the information. So, you also notice that there is a soft magnetic underlayer in perpendicular recording. Okay. So, this perpendicular recording technology uses this soft magnetic underlayer for writing information. Okay. So, before we go here, let me ask a question, then discuss further. Okay, I will use let us say you have a disc with a ferromagnetic particle, you want to magnetize the material to be like this. So, for this I told you that we can use a head like this, then this head will produce some field, and this field also will come out, and it can write magnetization to be right or left, right. You have a disc like this. Now, here you want to write the bits to be magnetized up or down. What kind of head will you use? So, here you see the magnetic field is going this way. So, it is horizontal. So, you can write horizontal bit. Now, you want to write vertical bits. How will you write? Perpendicular. How can you come and draw? Come. Last day we will have some interaction. Come here.
I mean the magnets align in that direction, north and south. So
Okay.
they will be directing.
I mean, how will you? I mean, I cannot understand what you are talking about. You have to come here, draw, and explain what is in your mind.
For the longitudinal, the direction is along this, so
Mhm.
this is north and south.
Yeah.
But to make it perpendicular, we need to have alignment like this.
Yeah. I mean, how will your head produce electromagnetic field? You have to use some electromagnetic field, right? I mean, electromagnet to generate magnetic field, that has to make the magnetization up or down. So, how will the head look like?
The external magnetic field should be in this or this direction.
Yeah. So, how will you design a head to achieve that? Okay. Anyone else? Okay. Thank you. Anyone else has? Yeah. Huh? Circular toroid type. Okay. So, you are saying that you want to have some toroid which will produce magnetic field in the vertical direction. Okay. I mean, in some sense, this is also toroid, right? Your coil is a. So, you mean like this?
This insertion controls the field structure. No?
Okay, maybe you come here and draw.
We having a toroid on this.
Mm-hmm.
So towards the center we have the field either in this direction or in the opposite direction.
Mm-hmm.
So could that work?
Okay, so that will produce a magnetic field, but where is the return path? Return path for the magnetic field.
In this.
We need some return path, right?
Yeah, in this like towards the center it will be the fields are in this direction, right?
Mm-hmm.
In this. If you change the current, the
So it's going to be like this, is it?
yeah.
Mm-hmm. Okay, thank you. So, in the very early version of perpendicular magnetic recording, what they did is something similar to what you suggested. So, you have a coil, then they have a ferromagnetic core, okay. Then the disc media. I mean, this is some kind of return pole or whatsoever you can say, and they keep the disc media like this. Okay. But the next question is, let us say you have a disc. So, I told you that the disc has two surfaces and both sides have magnetic film, and we are writing information on both sides. So, we store say 500 gigabyte of data here, 500 gigabyte of data on the other side. So, if you have a head like this, how will you write on both sides? So, when you try to write here, then it will erase the data here. Okay. How will you do that? Okay, so this was the first concept, I think 1980s, somewhere there. So, they realized that you cannot write on both sides of the disk. Then they came up with this concept called single pole head. So, now the head will look something like this. Okay, I told you that disk media has a soft magnetic underlayer. Okay, so, this is the layer that stores the information. So, storing happens here, but below this layer there is a soft magnetic underlayer. There will be some layer to separate these two. Let us ignore them for the time being. Let us just imagine that there are two ferromagnetic layers. Okay. So, this layer is a harder layer with a coercivity of say 6 kilovolts to store information. This is the soft magnetic underlayer with a coercivity, very low coercivity layer, say a few volts. Okay. So, when we talk about electromagnetic writers, again we are talking about some soft magnetic material as a core of the electromagnet. So, that is why I have used the same color code blue representing both the ferromagnetic core as well as the soft magnetic underlayer in perpendicular recording technology. They are soft material with a low coercivity, low resonance and so on. Okay, so, when you write information, you send the current through this head. Okay, it produces flux line shown by the yellow lines. Okay, so, this yellow lines will go through the soft magnetic underlayer like this. Okay, so, when you energize the coil of the electromagnet, it will produce a set of flux lines. So, magnetic flux lines always follow a closed path, right. So, they go through the recording layer, then this soft magnetic material passes them back to the other side of the head. Okay. So, this is how the writing happens. Okay. To give you some perspective of how beautiful this design is, let me also explain another concept. So, when we design longitudinal recording media, right, longitudinal recording technology, we have electromagnet, we send current. So, this current produces magnetic flux lines, the flux lines go through the gap, they also go through outside. So, we call this as fringing field. Okay. So, we are using the fringing field to write information. So, if you look at the values of the gap field and the fringing field, gap field is usually 2 times larger than the fringing field. Okay. Your field is more here, the gap, and your field here is less. So, we are using the weaker field to write information in longitudinal recording. Let us say you have certain material here, this can produce a gap field of say 15,000 Oster, fringing field will be like 7,000, 8,000 kind of Oster. Okay. So, we are using this 7,000 Oster to write information in longitudinal recording. So, we are not using, we cannot exploit the gap field for writing information in longitudinal recording technology. So, this is a problem. Now, let us come to the other design. So, in perpendicular recording technology, we have this kind of design. So, magnetic flux line go through this fashion. Okay. So, can you see something here interesting? What is interesting in this design? Pardon?
Strength of the field while writing.
What field?
That is strength of the field.
Is higher. Why?
Because we have concentrated it in narrow region.
Yeah. So, if I rotate this by 90 degree, okay, so I rotate this by 90 degree. Now, you look at this one. So, these flux lines look very similar to the longitudinal recording technology flux line, and if you notice the disc media, which is the black color, it is in the gap field. Okay. So, in perpendicular recording technology, by this, I mean, if I am rotating this way, right, but virtually we are using the gap field to write information. Okay. So, instead of the 7000 Oersted, what we have been using in longitudinal recording technology, now we have, with this design, we are using much larger field to write information. Okay, so, this is the design they came up with. So, by using a soft magnetic underlayer and by using a head like this, they can produce high magnetic field here. So, this magnetic field goes up or down. Okay. So, it will be either coming down, creating down magnetization, or it may be going up, creating up magnetization. Okay. So, this is how we magnetize the material to point up or down. Okay, so, this head is called a single pole head. So, before I describe this name, anyone sees any problem here? Magnetic flux line go through this region, magnetic flux line go through this region, any problem? If it magnetizes this region down, will it magnetize this region up? Because the magnetic field is coming this way, then going back this way. Right?
It is going in another direction, but it is very weak. I mean, flux through particular area is weak. So it
Okay.
will be enough to.
Yes. Okay. So, you know that the magnetic field strength is phi over A, right. The area here is smaller. So, you are concentrating more flux here. So, the strength at this point will be larger. You are producing large magnetic field here, but when it comes to this region, this part of the head is a wider, a large area. So, the flux is not that concentrated, your area is large. So, the magnetic field you produce here is not large enough. Okay. Okay. So, basically you are using only one pole for writing information. So, because of that reason it is called single pole head. Okay. So, even though you have two poles, effectively only this pole is writing information. So, it is called a single pole head, and this pole is called a return pole. The flux lines return via this pole. So, it is called return pole, and this is the writing pole. So, if you compare the field strength at this pole and the other pole, right. So, the writing pole may produce 15,000 Oersted, okay, whereas this return pole may produce a field of around 1500 oersted. Okay, it still produces some magnetic field of the order of 1500 oersted. So, because of this reason, when people design perpendicular recording media, they design the recording media in such a way that this field called nucleation field is more than what you see here. Suppose 1500 kind of field is seen here, you have to design recording media with a nucleation field of more than 2000 oersted. So, I defined this earlier. Nucleation field is the field at which like only 5% of magnetization switches, I mean 5% drop in MS. Okay. That means very few grains switch at nucleation field. Okay. So, what it means is that you are designing a media where this field does not reverse any grain. Okay. That is basically the concept. Okay, that is about perpendicular recording writing technique. Yeah, so, as I said, the disc will be placed somewhere here, the original configuration. Okay, to write on both sides, let us say you have 1 millimeter thick, you have one head here, another head here, but if I zoom in, both heads produce magnetic field that goes through this way and come back. Okay, so, similarly, this head will produce certain magnetic field, it will write bit, come back through the subtended layer to the other pole. Okay. So, this is how using a single pole head kind of head you can write on both sides of the hard disk. Okay, maybe I will just spend 5 minutes before break. Then after break we will go through the test question. Okay. So, I will satisfy both of you. So, I told you that we are using a sputtering machine with many chambers. That is because if you look at a perpendicular recording media of the current hard disk drive, you will find about 20 layers going from bottom to top. You will find 20 or more. Okay. I am not following the progress now, but I expect it should be more than 20 layers. Okay, so, these are the soft magnetic materials I described. So, the head produces certain magnetic field, it goes through the soft underlayer, then goes back to the other side of the head. Okay. So, you notice that this soft underlayer is not a single layer, it is again a SAF. Okay, so, you have some thin layer of ruthenium and you have at least 2 ferromagnetic layers which are antiferromagnetic coupled. So, here again we are using synthetic antiferromagnetic structure to minimize some noise which we do not go into detail. Then we have some seed layers which help these 2 ruthenium layers to grow with certain epitaxial texture. Over this we have many layers of magnetic material. Okay. So, when I said recording layer in the previous discussion. We assumed that one magnetic layer stores the bits, but in reality the recording layer comprises of many layers. So, you see the I put many layer. Okay, so maybe I will just focus on this one today, why we need many layers of recording material rather than just one recording layer. Okay. I will skip all the other part because we do not have time to discuss everything. So, we learnt about coherent rotation or Stoner-Wohlforth reversal mechanism, where I mentioned that if a particle has an anisotropy constant Ku and if the magnetization is m, wrong mouse. So, if a particle has an anisotropy constant Ku and the magnetization ms, then the anisotropy field required to switch the magnetization is Hk. Okay. So, if a particle has say 10 power 6 earth per cc, ms of 1000 or 500 mu per cc, you can calculate Hk. So, typical Hk of a hard disk media can be around 20 kilostat. Okay. Whereas, the magnetic field that you can produce by winding a coil and inserting a ferromagnetic core, you may be able to produce almost similar value. Okay. So, this is not much more than the anisotropy constant of the material. So, there may be some difficulty, I mean there may not there may be, there is difficulty to write information on materials with a large anisotropy constant. Okay. So, writing has always been a problem. So, people are trying to come up with various methods to write information. Okay. So, in that sense, if you follow this switching coherent switching mechanism, then you have this problem. Okay. What if you go to some other form of switching, which we call incoherent switching? Okay. So, this is the question people asked, then they came up with methods to achieve incoherent switching. Okay. So, when I described to you the coherent switching, I mentioned that let us say initially your magnetizations are like this. When you apply a reversal magnetic field, so at some point of time these spins will be at this angle, at another point of time they will be like this and so on, right. So, in coherent rotation reversal mechanism, all spins cooperate with each other, they switch together. So, all the spins, let us say you have a grain, cylindrical grain, all the spins in this grain are switching together. Okay. So, there is a harmony between them, like the synchronized swimmers of Olympic swimming, they all collaborate together. Okay. So, when we talk about incoherent switching, what we are discussing is like, let us say initially you are here, initially all the magnetizations are like this. Now, I apply some magnetic field. So, what happens is that this magnetic field changes the magnetization of the top spins, then the next layer spins are not that responsive to the magnetic field, then the spins at the bottom are like this. Okay. So, you see that there is no coherency like what you see here. The spins at the top behave differently compared to the spins at the bottom. Okay. At another point of time, maybe the spins at the top are like this, then this is like this, then this is like this. Okay. Then at another time, maybe these spins are the top are like this, then like this. Okay. So, you can see that the spins are not switching in a coherent manner, and this switching is called incoherent switching. Okay. So, the beauty of this switching method is that you can switch with a writing field much lower than the anisotropy field of the material. Okay. So, we can achieve this by having materials with two different magnetic property. For example, we can have a layer with a HK of 20 kilovolt at the bottom and 10 kilovolt at the top. So, you see the coercivities HK of the two materials that we use are different, or you can have many layers, or you can have a gradual increase from gradual decrease from 20 kilovolt to 10 kilovolt. So, gradually changing and so on. Okay. So, this kind of material where you have many layers with a different anisotropy field, they will switch independent of each other. Okay. So, it is like a domino falling down. So, let us say we have a set of dominoes like this. So, this video is not working. Okay, let us say we have a lot of domino like this. I push this one, what will happen? This layer will fall, this will fall. So, gradually it will cascade to the next layer. So, in a similar sense, when we have layers with various anisotropy, when you apply magnetic field, first this layer will respond, then that will have an impact on the next layer, and that will have an impact on the next layer, and so on. Okay. Okay, so, here if you look at the color code, initially all are red, means magnetization is pointing up. When you apply magnetic field, now you see this layer is pointing at this angle, this is still pointing up. So, you can see gradually the reversal happens. Okay. So, this layer reverses first and so on. So, this kind of reversal mechanism is called incoherent reversal mechanism. So, to achieve that, they have many magnetic layers. So, it is like you can have one magnetic layer here, another one here, another magnetic layer here, and so on, with various values of anisotropy field. Okay, so, that is why there are many layers. Okay, so, that is why I say here there are many layers. So, these layers help to achieve better writing of data. I have some very interesting video to show. Okay, maybe after the break I will show you. Okay. Now, we will have a break, see you later. Okay, so before the break, I told you that in the contemporary hard disk media, we have many magnetic layers. They are separated by some thin layers, and they are made up of layers with various anisotropy field or anisotropy constant that helps in achieving the switching of different magnetization layers. Okay. So, that concept can be better understood by looking at this video, where we are talking about a domino chain reaction. Okay. Let us watch the video.
Know is that a domino can knock over another domino, which is about 1.5 times larger. So what I have here is a chain of dominoes. Each one is 1.5 times larger than the previous one. And the smallest domino is about 5 millimeters high and 1 millimeter thick. And I will carefully place it. And there are 13 dominoes. And the largest domino, it weighs about 100 pounds and is more than 1 meter tall. Ready? Boom. That was 13 dominoes. If I had 29 dominoes, the last domino would be as tall as the Empire State Building.
Okay, here the first domino is falling with certain kinetic energy, right? How this kinetic energy gets amplified? Any idea? How this small tile can finally switch the large tile? Okay, anyway, the answer is here.
Here we go. What's the physics going on here? Well, every time you stand up a domino, you lift it against gravity. And that stores some of gravitational potential energy in the domino. And you only have to put in a little bit of push to get it to that tipping point. And then you get all that energy back again when it falls over. And that's more than enough energy to knock over the next domino, which releases even more energy. So it turns out the amplification in this series of 13 dominoes is about 2 billion. So we put in a little tiny bit of energy at the beginning, and we get 2 billion times as much out at the end. But of course, we put all that energy in by lifting these dominoes and standing them up again. So that's a kind of chain reaction. You trigger it, and more energy comes out, and more energy is released each step. Let's see it in slow-mo.
Okay, so this is just an analogy. The physics is not exactly the same. Just remember, this is only an analogy. So in a similar fashion, in magnetic recording media, we have layers with various anisotropy constant. Let me open. Just for easy understanding, that is an analogy. Let us say you have a layer with a large anisotropy field. Then say medium anisotropy field and a smaller anisotropy field. So, when you apply a magnetic field, so you are reversing the magnetization of this layer and that cascades to the next layer and so on. Okay. So, by having many layers with a different anisotropy field, and if a magnetic field is coming from this side, the magnetization reversal will cascade to the larger anisotropy layer. Okay. So, this way you can switch even materials with a large anisotropy field more than the field that can be produced by a writer. Okay. So, this is the concept of incoherent switching. So, this is one reason why we have many recording layers. Okay. So, you will notice that I mean if you look at the recording layer structure, so these recording layers will be like you have a recording layer, there is a spacer layer and so on. So, you notice that there is some spacing between these layers. Okay. So, these spacer layers control the exchange coupling between these different layers. Let us say the coupling between these layers are very strong. So, if the coupling is very strong, what will happen? Let us say these layers are tightly coupled. If you do something to the soft, what will happen? Huh?
So it will instantly.
So, if this okay, let me answer. So, if the layers are tightly coupled, you cannot reverse anything. Okay. So, you try to, I mean you apply magnetic field, you try to reverse the magnetization of this layer, but this layer is tightly coupled to this layer. So, it will prevent this happening. So, the magnetization of this layer is going to be like this. So, if the coupling is very tight, I mean if the exchange coupling between all these layers is strong, reversal of the whole stack will not happen. Okay, if these layers are completely decoupled, okay, they are not coupled at all, then what will happen? Only top layer will reverse. Okay. So, if coupling is too weak, only soft layer will reverse. Okay. So, you saw the domino video, right? Now, you know these results. Now, you come back to the analogy. So, what is the analogy for this in the domino case, and what is the analogy for this in the domino case? So, how will you explain this using the domino example?
Coupling is too weak means distance may be large when
Yes.
it falls it doesn't.
Yeah. So, coupling is too weak is like keeping the dominoes far away from each other. That means, when this domino falls down, it does not impact any other layers. Okay. That is the example for coupling too weak. Okay. This one too close, yeah, they are just next to each other. So, you have one domino here, another domino here, another domino here, like that. Now, if you try to push, you are trying to push this whole thing, okay? You cannot reverse. Okay? So, optimization of this exchange coupling is also important. It cannot be too weak, it cannot be too strong, then you cannot achieve the reversal. So, we have to optimize this exchange coupling. So, we have some layers to control the exchange coupling, and because of all these designs, right, we can switch the recording media. So, here I show you like 5 layers. Okay. So, 3 ferromagnetic layers, 2 spacer layers, but we can have more layers. Okay. So, depending on the number of layers you have, you can go even over 20 layers for hard disk recording technology. Okay. So, this is the reason we have so many layers for hard disk recording technology, and after doing all this research and so on, we are selling them for $7 US. Okay. So, that is the irony. Okay. So, with that we will move on to the next aspect, which is about the questions. So, you have part 1, part A, part B. Part B is set by me, part A is set by Subhankar and Atul. I don't know. So, if you have question in part A, you have to ask them. So, are there any difficult questions in part B? All have been already discussed, right? There are some new questions, no. So, can I say all of you would have scored 30 out of 30 in the second part? Percentile? Okay.
The students marks based on the percentile I have like prepared.
What do you want to show the percentile?
If you want like for your reference to see how many are correct.
Yeah, okay. Yeah.
This is how it happens in our college.
Mm-hmm.
So nothing there like 1 second. So this is the maximum marks out of 50. They have to do 50%. So based on 50%, how many they have got. So based on what percentage they have achieved. So above 90%, that will be AA, 10 CPI. 80 to 89 will be 9. So it will be AB. Then BB, something like that.
I mean, do you have any profiling for like which are the tough question or?
Which are the tough questions?
Yeah. Do you have something like that? I think this one we don't need to show them now.
Yes.
Yeah.
That also, if you like how many.
This one we will discuss after Tanmay comes.
Okay.
Yeah. Okay, so now let us make it free floor. Any questions on the topic that we have learnt, then we can discuss, or any concepts that were difficult. So, when I taught you it was difficult to follow, but now you want to revisit and okay. Okay, so here I have so many layers. So, the question is about why do you use lubricant. Okay, so anyway, so since the question is on lubricant, let me explain the purpose of all the layers. Okay. So, we have a substrate and we are depositing so many thin layers. Okay. So, if you deposit many layers on top of a substrate, then there are possibilities that the films do not stick onto the substrate. Sometimes your films may peel off. Okay. So, if you any of you are doing sputtering or some device fabrication, sometimes you might encounter the problem of films from peeling off. Okay. So, usually we start with the layer which improves the adhesion of all the layers onto the substrate, and in the hard disk drive technology, this is usually tantalum, titanium or some alloys of titanium or tantalum. Okay. So, this layer is meant for improving the addition of so many layers onto the disk substrate, and this you already learned, right. I mean, you want some solid platform to hold all the layers at the top. So, that is why we have a substrate. Then soft underlayer we learned that the magnetic field produced by the head comes all the way to the soft underlayer and goes back to the head again. So, this soft underlayer provides a conducting path for magnetic flux that comes from the recording head. So, flux goes through all these recording layer, write information, then it goes back to the head. Okay. So, this is the soft underlayer and it has an synthetic antiferromagnetic structure through some thin ruthenium layer. So, this ruthenium layer is typically 0.8 nanometer. Okay, 0.8 nanometer ruthenium we deposit to achieve the synthetic antiferromagnetic property, and the purpose is to reduce the noise that comes from soft underlayer. Then we have a few layers like nickel tungsten, ruthenium and 2 ruthenium. So, all these ruthenium layers help to provide some crystallographic texture, so that the easy axis of the other layers on top, the cobalt layers will have easy axis, C axis in the perpendicular direction. Okay. So, these are all cobalt material, right. Cobalt has a HCP 002 direction is the C axis. So, this will be in the perpendicular direction. So, one reason of having so many layers is to achieve the C axis in the perpendicular direction. Okay. So, by tuning this one, you can maximize the number of grains which will have the C axis in the perpendicular direction. Okay. If you do not have, or if you do not optimize these layers, so you will have some grains with a C axis like this, some grains with C axis like this, and so on. Okay. So, you will have some randomness. To minimize that randomness and to make more grains to have C axis in the perpendicular direction, people optimize all these layers. Okay, then we already learned this one. So, we have many layers to improve the writing process. This one we skip. Okay, we skip this one. If anyone is interested, I can teach you. Then later we have, you see, 2 carbon layers. So, these are carbon layers. So, this layer prevent all the other layers at the bottom from getting corroded. Okay. So, the carbon layers are meant for corrosion protection. So, if any of you are working on thin films, so typically you may use some layers as a capping layer, tantalum, platinum or some such layers you will deposit on the top to make your films from getting corroded. But in the hard disk industry, we use a carbon layer to prevent the disk from getting corroded. Okay, so why we have 2 carbon? So we have one carbon with this carbon is deposited with some hydrogen during the deposition. The second carbon is deposited with some nitrogen during the deposition. Okay. So all these are sputtered, all these layers until the top carbon layer all are sputtered. So when we deposit the second carbon layer, we deposit the carbon in the presence of some nitrogen gas. Okay, so why we have 2 carbon layers is because the first carbon layer, it has a good coverage. Coverage means it will like spread over the disc uniformly, and it will have no pinholes. So it's good for the corrosion protection. Okay, the second carbon layer with nitrogen is needed for something called lubricant affinity. Okay. So we design this layer with the idea that we are going to have some lubricant at the top. Okay. So this carbon, nitrated carbon, has some chemical property that enables the lubricant to stick to the carbon very well. Okay. Otherwise, what will happen if you have a disc? Let us say I have a disc. So there will be some regions where the lubricants will stick very well. Some regions the lubricant may not stick very well. Okay. So you want the lubricant to stick very well. Okay. So if you want the lubricants to be not in patches like this, but you want them to be uniformly spread, then we have to grow this nitrated carbon. Okay, then on top we have lubricant. Okay, so this lubricant is or some polymers like the chemical name is called Zidol. If you are interested in the chemistry, you can look for this name. You can Google and find out what Zidol is. Okay, so why we have this lubricant is because, as I mentioned, we are rotating a disc at a rotational speeds of like 5,400 or 7,200 rotation per minute, which is a high speed rotation, and we are flying the head on top of it at a spacing of 1 nanometer. So, imagine you are rotating something at very high speed and you are flying at 1 nanometer. If there is some occasional contact, then the head can crash, it can crash these films. Okay. So, to prevent the mechanical crash, things like that, we have this lubricant. Okay. So, this lubricant, this whole thing helps to minimize the problem that arise when there is a crash between the disc and head. Okay. Any other questions? Pardon? Carbon is sputtered, yes. Okay, I told you until this is sputtered. Okay. I told you that until the carbon is sputtered, lubricant is not sputtered. Okay. Lubricant is deposited in some other technique. Let me show you. So, there are two ways to deposit the lubricant. So, one way is to do dip coating. So, in the case of dip coating, you slowly dip the lubricant, the disc into the lubricant. So, all these the lubricant molecules will go and stick to the disc, then raise the disc slowly, then your disc is coated with lubricant molecules. So, this one way, this is called dip coating. So, in another coating what they do is like they dip the disc into the disc, then they will drain the liquid, the lubricant. So, the lubricant will be drained away, then your disc is coated with the molecules. So, except for the lubricant layer, all the other layers are deposited by sputtering. Okay, since you are interested in this one, you better watch this video. So, this video shows so much the high tech involved in hard disk manufacturing. Okay, let us play this one.
We design them to become your closest friends. Reliable, compatible, responsive. Amazingly smart. You might take them for granted, but they hold your stories and memories, your pictures and videos, your music. You trust them as business partners and rely on them to provide your entertainment, knowledge, and communication. The Seagate family of drives. We'd like to share with you how we've provided more than 1 billion drives to people around the world. A glimpse of the inside story. Every Seagate drive is comprised of sophisticated components. Recording heads, recording media, electronics, and firmware, all playing a critical role in the storage of information. We have hundreds of scientists and experts in everything from chemistry, physics, and process technology to fluid mechanics and aerodynamics. These specialists design and build the world's most advanced digital storage products by combining their collective expertise. All of the information stored on a hard drive travels through the recording head. This tiny electromagnetic wonder hovers less than 100 atoms above the disk, a gap 100 times thinner than a sheet of paper, reading and writing information on a surface spinning up to 15,000 revolutions per minute. To build these advanced recording heads, silicon wafers are sectioned into increasingly microscopic pieces, attached to mechanical arms called suspension assemblies. These heads are so small that Seagate's thousands of square feet of clean rooms need to be 100 times cleaner than a hospital operating room. Seagate engineers put these recording heads through rigorous testing, screening, and precision measurement before they are positioned in a hard drive. Recording media are the spinning disks that store the information on a hard drive. These disks are manufactured starting with substrates, typically made of glass or aluminum. Then, microscopically thin layers of highly specialized magnetic films are applied, enabling the storage of all those trillions of zeros and ones that make up the digital content. The disks are also polished and lubricated before a multi-disc writer applies servo patterns onto each media surface. These servo patterns create a map that determines where all the digital data can be located. The disks are now ready to be integrated into a hard drive.
They all are robots. Nobody is using hands.
This is where Seagate engineers bring together all of the heads and disks, integrated circuits and motors, software and firmware, and other critical technologies. Assembly begins with base decks, including the motors that spin the disks. Each deck has an electronic tag, similar to a digital fingerprint. that tracks the drive from assembly to testing and also stores key information. Precise and fully automated machinery combines the sophisticated components for each drive. Parts are assembled, balanced, measured, and adjusted according to demanding tolerances. Then, in their state-of-the-art automated testing systems, Seagate can analyze more than 1.5 million drives at a time. These drives will undergo thousands of tests to make absolutely sure they meet our customers' exacting criteria. Our drives are put through procedures that push them beyond reasonable limits in all phases of a drive's development to make sure they run smoothly in all kinds of systems and demanding environments. From an acoustic vault to help us eliminate noise, to chambers that simulate altitudes up to 40,000 feet and pressures well below sea level, drives are cooked to extreme temperatures. We shake and drop them and hit them with thousands of power on and off cycles. Seagate scientists keep dreaming up new ways to test the limits, all with the goal of making sure those drives perform as promised. Seagate is leveraging more than 30 years of leadership in hard drives to develop the next generation of storage technologies. Solid-state drives and hybrid combinations of solid-state and traditional disk storage are already being delivered to customers worldwide. And we continue to push the limits of rotating hard drives with discoveries such as heat-assisted magnetic recording. The future demands increased capacity and faster performance, and this is just the beginning of what's going on in our R&D labs to meet the world's insatiable need for digital storage. Over the next year alone, people and their computers will generate 40 exabytes of new information, the equivalent of 700 billion hours of music, or 13 trillion digital photos. That's a lot of hard drives needed. Hundreds of millions of them. Seagate meets this unprecedented demand through customer-focused innovation and operational excellence. Building 6 hard drives, hybrid drives, and solid-state drives every second. And every one of those drives journeys through more than 1,000 manufacturing steps, flawlessly calibrated to provide the most reliable and consistent supply chain for the more than 1 billion devices delivered to our customers worldwide. Seagate is building the performance, reliability, and quality you depend upon, so you can store, share, protect, and enjoy your digital life.
So you can see the complexity involved in making a hard disk drive. To give you some perspective, right? So we learnt about read sensors. So in the hard disk drive, read sensor and the writing head are in a same place, okay, next to each other. One for reading, another for writing is called integrated head. So to make this integrated head, the number of processes required, the process steps, right? For example, you clean substrate, deposit some resist, spin coat, then expose, lithography, etching. Let us say these are some examples of process steps. The number of process steps involved in making a head is more than 400. Okay, more than 400 steps are involved in making a head, and it takes, let us say you start this whole processes on day 1. To finish all the process steps, it takes 3 months. There are so many processes. So you start making a head, then after 3 months your head will be ready. So that is the kind of complexity involved in making a head for reading, writing information in hard disk drive. And suppose you want to start a company. Let us say Ambani wants to make a hard disk drive company. Then he has to get 200 patents cleared before he can make a hard disk drive, because there are so many patents cover each aspect of hard disk drive. You make magnetic recording, we saw that there are 20 layers. So, there will be maybe 20 patents just for the hard disk alone. Then you take the head, there will be so many patents. So, like that, like there are 200 different technologies you need to make a hard disk drive. Recently, one company from China, they contacted me and they said they are interested in jumping into hard disk drive. Then I told him that these are the problems. Okay. So, it is very highly complex technology. You won't realize, you may buy a hard disk drive for $100, you think it is cheap, but there are so many things, physics, material science, as you would have listened in this talk, right. So, they said, for example, you talk about head flying onto the disk. So, that is fluid dynamics. So, mechanical engineers have to simulate how the aerodynamics of a head flying over the disk will look like. Then chemists are involved in the lubricant, physicists are involved in designing the head media, so many things. Then electrical engineers are writing the coding, signal processing, mathematicians come in and things like that. So, hard disk drive is a completely interdisciplinary field. Okay. So, so many scientists come and work together to make a hard disk drive work. Okay. Any other questions?
One question from online.
Mhm.
Can you please explain the synthesis of substrates in industry?
Can we revisit this one? Oh, different one.
Can you please explain the synthesis of substrates in industry?
What of substrates?
Synthesis.
Synthesis of substrates. Okay. If we are talking about, okay, depends on the industry we are talking about. I had a lot of slides, but I deleted. So, depending on the industry, we may use different substrates. So, in the semiconductor industry, we use silicon substrates. Semiconductor industry, we have silicon substrates. So, I am not very expert in this silicon technology, but basically it is like you have a seed of silicon, then on this silicon you grow the silicon crystal layer by layer. Okay. So, finally, you will have a large piece of silicon. Okay. So, people will cut them into thin wafers, then these thin wafers will be polished to make the substrate for the semiconductor industry. So, many research labs also use silicon substrate for their making their sample. So, this is one type. So, here is like it is basically crystal growth. You grow silicon crystal, then you slice them, polish and achieve the desired dimension. Okay. So, that is the process in silicon. So, in the case of hard disk drive, we have two types of substrates, aluminum alloy or glass substrates. So, here again aluminum alloy you can make by melting. So, let us say you have a sheet of aluminum alloy, then you cut them into disc. Okay, so you make disc out of this sheet of aluminum, then you polish them. Okay, so you have to polish to a roughness of around 0.15 nanometer. Okay, so yesterday when I went around the posters, so some of you have had roughness of 3 nanometer, 4 nanometer, and you said that that's a very low roughness. Okay. But in the industry, if you take the semiconductor technology or hard disk drive technology, we are looking at roughness of 0.15 or below. Okay. So, again why we are looking for small roughness is because if average roughness is 0.15 nanometer, the peak, so you will have the disk, so somewhere you will have some peak, right. So, this peak will be roughly 0.5 times, 5 to 10 times. Okay. So, we want to make this as small as possible, so that your peak roughness also is not that high. So, we are talking about a head flying over 1 nanometer height. Okay. So, we have to minimize the roughness to this very low value. So, if I say my roughness is 0.3 nanometer, then my friends from Seagate or Western Digital, they will laugh at me. Okay. This is not good enough for application. So, we make the disk to have very low roughness. So, that is where a lot of polishing and things like that are done. So, similarly glass also is like that. So, you make glass into this shape, then polish. So, glass polishing is very difficult, but there are some benefits. Okay. So, when you polish glass also, even though it is difficult, you still need to achieve this kind of low roughness. Okay. So, to give you some perspective, so one famous company which makes ceramic plates, okay. So, they came to meet us that they want to enter into hard disk industry. Okay. So, they wanted to make ceramic substrates for hard disk application. Okay. So, they sell plates which people buy at home and use. Okay. So, their main business is home business. Okay. They thought if they enter into hard disk drive, so typically we make like 500 million disks every year, 500 or more million disks every year. So, this is a huge market. So, this company wanted to enter into substrate business, make substrate and make money. Okay. Then we told them the process steps involved in making a glass substrate. So, how much polishing, what is the roughness needed, all those things. Then they gave up. Okay. It is not easy. So, it is like ceramic plate, what they do, they just do some processing, they sell the plate for $15. But if they have to make ceramic substrate, they need to so much process, achieve this kind of roughness, then they will only sell for $7. Then they thought it is not a good business. Okay. So, this is the kind of complexities involved in technology. There is another online question, can we revisit to understand why a high damping constant is undesirable? What I understand is that higher damping constant will result in faster alignment of magnetization along field direction and hence better speed, which is in contrary to the discussion in the sessions. There is no contradictory. I told you that there are benefits and problems. Okay. So, with high damping constant, the benefit is high speed, which I told you already in the lecture. I told you that if you have high damping constant, you can achieve high speed. So, this is the benefit. Okay. So, what I said in the class was that if you apply certain magnetic field, then damping makes the magnetization to be aligned with the magnetic field soon, very soon. Okay. So, with very short time scales you can align the magnetization along the direction of the field. So, high damping constant means high speed. So, this is the benefit. But high damping also has a problem. So, the problem is if you look at the formula for the current density required to switch the magnetization. So, that will also be proportional to alpha, okay, proportional to damping constant. So, this alpha is now proportional constant. So, I will use word damping constant, otherwise I will write 2 alpha. Okay. So, now J C, you will notice that the J C is proportional to the damping constant. So, what it means, if your damping constant is high, you need more current to write information. That means, you spend more energy to switch the magnetization. So, it is good in one sense and it has a problem in another sense. Okay. So, you can look for the formula about switching current, then you will realize this. Okay. So, what you heard is right, but you heard only one aspect of damping constant. There are 2 aspects to damping constant. Okay. Any other questions? Okay, anything else? I mean, until Professor Datta comes, we can discuss. Yes. What device? MTJ device. Okay.
So if the fixed layer thickness we increase, if then our polarization efficiency will increase. So is it proportional or there is some limitations as well?
Okay. So, you are talking about STT-MRAM. Okay. There may be some gain if you increase the thickness of the reference layer, okay. But beyond certain point, what happen, there are 2 problems. Okay. Let us say you make it like only 1 nanometer, then you may not achieve sufficient spin polarization, that is a problem. But from 1 nanometer, let us say 5 nanometer or 10 nanometer, there may be some significant gain, but if you go beyond that, there may be no gain. Okay. So, if you go to very large thickness, there may be no gain. Okay. So, I do not have the ready made answer, but my thinking is 2. Okay. So, first problem may be coming from the spin diffusion length. Okay. So, only for certain spin diffusion length, that will determine what is the thickness where you will have more gain. Okay. So, that is one thing. So, it will be decided by spin diffusion length. The second problem is from the manufacturing. So, let us say you make it very thick. So, what people do, they have many layers of MRAM material, then they have to do lithography. So, we have certain resist. Then using this resist as a mask, you are etching the layers to get the MTJ, right. So, if your MTJ layers are very thick, you will have difficulty. I mean, you may have to grow like very thick resist layers, and etching will become a problem, okay. Especially when you are packing MRAMs at a closer distances, how you etch so thick layer and whether you can get the desired pattern. I think all this manufacturing problem will be happening. So, these two will limit how thick you go.
So is it like if the thickness you kept increasing, the polarization efficiency will saturate or it will decrease after some point in time?
That I have no idea. I have not read about it. So, I cannot comment on that. Yeah, you can look for the answer somewhere. Yes. Anything else?
Can you explain the GMR CPP configuration also?
GMR CPP configuration. Okay. Okay, let us say we form a few layers. Let us just take 3 layers for example. Okay. So, you have 2 ferromagnetic layers and a spacer layer, and they are in certain shape. Okay. So, when we are talking about current in plane, we are talking about current going through this way and coming out. So, when we talk about current perpendicular to the plane, we are talking about sending current through the layer. Sorry, this is I. Okay, so this is current in plane, current perpendicular to the plane. Okay, so I mentioned to you that the CPP becomes useful only when the device sizes are smaller. Okay. Okay, that is because let us say if this whole thing is very large in area, so when the device is very large, you try to measure the resistance, you will find the resistance to be very low, right. Large sheet of magnetic materials you try to measure. So, basically we use something called RA, resistance area product, to define the GMR TMR sensors. So, let us say we have some RA value, you divide by a large A, then what you will end up with some low resistance. Okay. So, this is the problem. We could not use the CPP at high density data storage, where the sensors were bigger, but once you go to small size, you have a reasonably larger resistance. So, let us say this is a 10 ohm. Okay. So, if the GMR is 10%, your resistance will go from 10 ohm to 11 ohms. That is reasonable, but in this case, for example, the resistance may be like 0.1 ohm or 0.01 ohm, then the change will be like only 0.1 to 0.11 ohm, something like that. So, the difference is now 0.01 ohm, which is too small to read, whereas here 1 ohm is easy to read. Right? So, because of this reason, CPP was not useful at low densities. Early days of hard disk, we were using bigger heads, so it was not useful, but when we go to high density, we are making the heads smaller and smaller. At that point of time, this becomes useful. So, that is one thing. Second reason why CPP is useful is because in hard disk we have some shields, right. So, between on both sides of the read sensor you have some shield. Let us say here we have some shield material. Shields are basically soft magnetic materials like say nickel, iron or something like that. These are metallic. Okay, so, similarly at the bottom also you have some soft magnetic material like these, which are magnetic and metallic. So, you can send current through the shield, through the device, and it will come through the other side of the shield, and because of this reason you are minimizing the spacing between shield and shield. Okay. Shield to shield spacing is reduced. So, this also helps to achieve high density recording, whereas in the case of CIP we have some shield here, we have metallic layer here, metallic layer here, and you do not want this current to be shunted by this metal. Okay. So, it may be shunted by this metal or the other metal. So, you have to grow some insulating layer. So, this insulating layer adds to the distance. So, the shield to shield spacing increases. So, this is a problem. So, what was your specific question here?
No, the configuration.
Configuration. Okay. Any other questions? Yes.
Can you tell about the D0 ferromagnetism?
D0 ferromagnet, I have no idea. Maybe you can teach us. Okay. I don't know. I haven't read about it. Magnetism itself, there are too many things, so wide knowledge, we only know a little bit. Okay, maybe something off topic, non-physics. So, when I was, you remember that day I duplicated a slide and I was trying to make a figure bigger than what was in the slide. Then I was spending a lot of time. Do you know why? Okay. So, what I was trying to do was to keep the aspect ratio of the image same. Okay. So, what is the aspect ratio? Let us say I have certain image. So, this image has 400 pixels in this side, 300 pixels here, and currently this picture occupies say 3 centimeter times 4 centimeter area. Okay. So, now I want this image to occupy a bigger area. Okay. So, when I do that, I should make that a multiple of this one. For example, I can make okay, what is the number I can say? Yeah, 9 by 12 or something like that. So, let us say I zoom in, then finally, one side is like 9 centimeter, another side is 12 centimeter, that is correct aspect ratio. So, this ratio is still 3 times 4, right. So, this is called aspect ratio. So, whenever you deal with figures, do not change the aspect ratio. Okay. So, you have to keep the same aspect ratio. So, quite often I see, especially among the Indian students, that you do not give any respect to this aspect ratio. For example, if a person is like this, okay, so either you make him like this, like a cartoon or like this. Okay. So, either you press on one side or compress on the other side and make him a cartoon. Okay. So, this is with people, and it happens with so many things. Yesterday also I saw many posters where the poster is supposed to be of this size, but during the printing or something the poster got elongated like this in one direction. So, all the fonts were, let us say if A is supposed to be like this, A was like this. Okay. And some cases GIAN was like this. Some cases GIAN can be like this. Okay, this is not correct. So, this I see quite often in India. So, respect the aspect ratio, maintain whenever you deal with pictures, maintain the same aspect ratio. Okay. So, here is 3:4, right. So, when you make it bigger or smaller, you should maintain the same. So, in PowerPoint you can do that. I could not do it here because I was dealing with the website, but with the app you can do that. So, if your friends do, educate them, okay? Educate them to have same aspect ratio. And another point I want to suggest about the poster presentation, that when you are creating a poster, right, when you create a poster, there may be people who are near the poster, some people may look at your poster from far, all should be able to see. Okay, so if you want all of them to be able to see your poster, the minimum font size this one no need to record, all off topics. Okay, so if you want all of them to see your posters, the minimum font size, the height of the font, for example, let us say you have A, letter A, this font has to be like 1 centimeter tall. Okay, so in the case of printing technology, 72 point means 1 inch, which is 2.454 centimeter. So 1 centimeter is equal to roughly 30 point. Okay. So in PowerPoint and Word you are using points to define your font size, right. So you use at least 30 point or 32 point when you design poster. Okay. Don't have too much text, thereby making your letters too small. Okay, I saw posters with 14 point or so. Okay, this is not good. So your poster should have fonts of this size, roughly at least. Sorry?
Stop the recording.
Yeah, they can stop.
Like you have to first formally conclude, like online participant, because this recording.
Oh, okay, it's okay, it's okay. Yeah, it's okay, no problem. Okay, any other questions or discussion? Okay, since we have nothing much to discuss, let me take another feedback. Okay, now we are at the end of the course, so please give the OCLAP feedback again. Okay. So we took one during the middle stage, so let's do one more. Okay, so please join. Okay, let's start. Okay, next one. next one. Next one. Next one. Next question. Okay, next question. So, for the online audiences, you have missed the neuromorphic computing discussion. I will share you some other YouTube link which you can watch and learn about neuromorphic computing. Okay, I will wait until 25 and move to the next question because it is taking too long time. Okay, I will just wait for first 20. Okay. So, once 20 people answer, I will move to the next question. Now the answers are coming rapidly. Okay, next one. 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 Okay, next question. Next one. So, last two questions. So, this is the penultimate question.
After this, like if family just say that that's it for today, so we'll just remove the online participants and for offline we can proceed further.
Okay. Tanmay said there's is coming in a few minutes, so we can wait, right? Yeah. So you mean they can go?
Recording will be continued till last night. So I think. These online participants, you can just ask them to leave.
They can leave, right? Yeah. So, all the online participants may leave now. Okay, if the online participants are listening, you may leave now. Okay. Okay, so this will be the last question. Okay, thank you. So we will wait until Professor Tanmay Dutta comes. Until then, we can discuss if there are any more questions.
I can announce that the certificate distribution will be happening.
Pardon?
So I can
Yeah,
announce
yeah,
that. I can announce that.
Mm.
So we have to wait till the Tanmay Dutta comes here. So after that we'll distribute the certificates also, and then we'll have the lunch here on the GIAN. So today there will be lunch at CET, okay, for all the participants. And then if you have anything to ask, like apart from this course also, you can discuss with sir. Okay.
Okay, I can show you some more videos which I skipped during the course because of lack of time. Okay, so in hard disk industry, right, especially the disk media industry, we are making something like 900 disks per hour. Okay, so if any of you are doing sputtering or any thin film deposition, so you know how much time you take to make one sample. Okay, you may take 1 hour to make one sample, or maybe you may make 2 or 3 samples per day. Okay, but the hard disk industries operate at 900 disks per hour. Okay, so how we can make 900 disks in 1 hour is through this kind of process. For example, I told you that there may be like 24 chambers. So in a disk sputtering system, you have like many chambers, 1, 2, 3, all the way to 24 chambers. So the disk will go in and come out like this. Okay, let me play the video. So the disk goes in, deposition happens in station 1, then the disk goes in, deposition happens in disk station 2, and so on. So by that time this has reached 2, right, another substrate will enter. So all these substrates go in queue one after another. So when this disk is in N, there is another substrate here, another substrate here, and so on. Okay. So all the disks go in sequence, and if let us say in each chamber, I mean the time taken for a disk to go from one chamber to the other chamber is only 4 seconds, for example. So within 4 seconds the sputtering happens and the disk has moved from one chamber to another chamber, for example. Then we can have 900 disks per hour, because every hour has 3600 seconds, right. So this is how the hard disk industry can achieve high throughput. Throughput is basically how many disks you can make an hour. So this is the sputtering machine we had in our lab. This is a production sputtering machine, old production type of machine. So here you will notice that we have loaded the disk here. There is a disk you can see here. So that disk will spend some time here, sputtering happens, it goes to the next station, sputtering happens, it will go to the next station, sputtering happens. So here, for visual idea of what is happening, we have opened this chamber, but during the sputtering there will be a door, this side door, this will close. So that door also has another target. So in hard disk media we have 2 targets, so 2 guns. So the deposition happens from this target and this target also. So when the disk goes in between 2 targets, both sides will get sputtered. So by making this kind of process, we can achieve many disks in every hour. Any other questions?
Sir, any more suggestions to make a better poster presentations? I mean, this font size and aspect ratio.
Okay,
Background.
font size, aspect ratio. I mean, usually aesthetics cannot be taught. Okay, so I don't know how to teach aesthetics, but you can all try to. So even with my students, quite often I tell them to change the colors. So my default, I mean, whenever you guys try to plot a graph, you are probably using origin, and origin throws in black, red, green. Okay, so all the graphs come in black, red, green. So my rule of thumb is never use black, green, red. Use some colors different from that. Then there are, I mean, if you want to use colors, right, there are many color templates. So, for example, so if you are publishing in some journal where you want to make your images to be, I mean, distinguishable even for people who have color blindness. So you can go and come with some template like this. You can use these colors for your graphs. And another thing is, like these days worldwide people don't use the serif fonts. For example, Times New Roman, hardly people use it. So people suggest using either Arial or Helvetica, those kind of font, for example. Arial, you know, okay. Arial is one type of sans serif font. So Helvetica font will look like this, So people are using this kind of fonts. So, but quite often I see here people always use Times New Roman. Okay, Times New Roman is so boring font. So these are sans serif fonts, you can use them. And in poster presentation, one point is that, like, okay, suppose the listener comes. Listener may have 2 minutes or 3 minutes, 5 minutes, or he may have interest only in certain aspect. So you should be able to tailor your presentation to suit the listener. So you cannot have like only one way of going from introduction all the way to the conclusion. You should be able to fragment and just focus on your presentation tailored to that particular customer. Okay. The color contrast also is some issue. So sometimes people will use dark color background, and the font they also use will be dark. Okay, that then people cannot see. So you have to use, if your background is dark, then the font has to be light, white, yellow, light yellow. Okay. Okay, another point maybe I can say is like when you guys read paper, right? When you do literature survey, you read papers. Usually, you read with the aim of understanding what is there in the paper. Okay, that's okay to start with. When you are a PhD student, you can do that. But at some point of time, your thinking should be not in exactly grasping what is written in the paper. Your thinking should be like halfway through. You should be what if you should come up with some idea. So the paper you read should trigger some idea that should form your paper. Okay, so you are reading paper not just for understanding everything what the authors have written, but it is for triggering some new ideas. So when you listen to talks also, you can daydream a bit, come up with some new idea. Okay, so that should be your goal. Only then you can be some kind of innovator. You can have new ideas for your paper.
So, what new materials do you think can be explored in this spintronics or magnetism related?
Okay, so there are many materials. So some people are interested in something, some people are not interested in something. So in my case, my group, we are looking at orbital torque. Okay, so so we learnt about using spin orbit torque to switch magnetization, right? So now we are still working on this one, but we are also looking at using orbital Hall effect to switch magnetization. So the beauty of this is that I mean theoretically it is claimed that orbital Hall effect is much larger in magnitude compared to spin orbit torque. So if you can convert orbital torque to spin, then you can use this spin to switch magnetization. So this is one area which I am working on, my team. Then another area that we in our group we are working on is alter magnets. So these are new form of magnetic materials people have proposed. Yes.
What does it mean converting orbital Hall into spin? And how do we
Okay. So the problem is okay, if you call L the orbital moment, orbital moment does not interact with the magnetization or magnetic moment. Okay. So you need some intermediate thing, so that you can use this to switch magnetization. Okay. So this is a bad example, do not use. See dark background, I am using red color, you cannot see. Okay. So we want to switch magnetization using orbital magnetic moment is not possible. So what we do, we use the LS coupling. So you know that orbital moment and spin moment can be coupled, and we have learnt so far in many lectures that we can use spin to switch magnetization. Okay. So when we talk about something like this, to give you practical example, let us say chromium is a orbital material, let us say there is a orbital Hall effect in chromium. So this chromium will have some orbital torque, some kind of L will go up, some kind of L will go down, but this L cannot switch the ferromagnetic layer. So what we do, we use some materials like a thin layer of platinum. Okay. So platinum has heavy spin orbit coupling. So this is spin orbit coupling, right. So platinum can convert L to S. So because of this platinum, now spins are coming into ferromagnetic layer and they can switch magnetization. So that is what I meant by SM like that. So just depositing chromium on ferromagnetic layer, you cannot switch magnetization, but by using some metals like platinum, you can convert the orbital magnetic moment into spin magnetic moment and use this spin to switch magnetization. Okay. Anyway, thank you all. So, I enjoyed interacting with you all the time. So, thank you very much. Okay, done. Questions, I mean, they said it's all easy. So,
Okay.
no point, yes.
They find it easy means they have learned.
Yeah, yeah.
Okay. Good afternoon, everyone. As we come to the last part of the last chapter of this wonderful sessions, where we have lot of learning, discussions, and lot of knowledge sharings. So now it's time to express our gratitude and appreciations for the active participants, and to bring this session to a formally on a closed session. So we are honored to have Professor Harshal B. Namade sir, head of the Department of Electronics and Electrical Engineering. I would like to request sir to please come on the stage and express few words with the audience.
Distinguished guests and participants, I hope you have enjoyed the course. At the same time, you had enlightening experience learning in this emerging field. I'm sure, I don't know whether you know or not, Prof. Prem has been diligently working on this topic and preparing notes and course material for you for this 10 days, day and night. Even Professor Dutta had sleepless nights preparing the course material. So I thank them for dedicating devotion. Okay, so finally I would like to request you to provide the feedback. So in the feedback form, just don't tick. So we would expect you to write a few words, because you can express better when you write in words. Okay. So I thank Professor Prem for coming to IIT Guwahati, and I expect that we will have more meetings, and you keep coming and updating us in this with the new new innovations and ideas in this field. Okay. Thank you, all of you. Bye.
Thank you, sir, for expressing your words. Now I would request Professor Prem sir to please come on stage and share his experience and some feedbacks for our participants along with this journey.
So, good afternoon, Professor Namade. Good afternoon, Professor Dutta, and all the students. So, I had very fun full of 10 days. I enjoyed interacting with you. I hope you also enjoyed listening to the lectures. I hope it was fruitful and you have learned some new topics and gained new knowledge. So at this point of time, I'd like to thank Professor Dutta for inviting me. So we know each other for close to 10 years now. And I also would like to thank all the volunteers like Atul, Subankar, and many other colleagues from Professor Datta's laboratory. And also I'd like to thank all of you for most of you are very keen in learning. So that's actually the most satisfying thing for a teacher. So if you all ask question and if you show passion to learn, that is the most fulfilling thing for a teacher. So I really felt with all of you. With that, I thank you all. Thank you very much.
Thank you, sir, for experiencing your words, and thank you for taking this course and sharing a lot of knowledge with us and with our participants. And we would expecting more interactions with you in future. Now I would like to request some of the participants to come on the stage and can share their feedbacks or some experience, whatever they have gone through in these 10 days. So any one of you or two of you can come on the stage. So no one wants to express something. Can come, anyone can come and express their words if want. No, I think someone can come and.
I'll throw this arrow.
So the spin will decide. Okay, if not coming on stage, you can just share words by standing there only itself. Sipra in the last.
Would also come here and speak if you would like.
Yeah, I don't mind, but
Please come.
Hi everyone, myself Shipra. I'm currently doing my PhD from Center for Nano, and my background is optoelectronics. So basically, I have no idea about magnetism and all. So it's been so long after my masters, I've forgotten all the concept and everything. So just to refresh my understanding, I joined this course, and it was so enriching. I learned a lot of things about magnetism and all, and also about the new discoveries and what work is going in terms of research. And I also feel I can somehow, I can also with other people, I can somehow relate and correlate my work. So it will be, I think, fruitful for my future. So yeah, thank you all. Thank you, sir. It was like really nice. You were like a really great teacher. Thank you.
Thank you, Sipra, for sharing your experience and the learning things you have done in these last 10 days. So I would like to request any other participants if they want to express something regarding our Prem sir or regarding this course or the course coordinator, Tanmay Dutta sir. Anyone, if they can come on stage or they can share from there only. We can pass you the mic if you are afraid of coming.
Come here.
No mic, बोले mic दे दो.
Mic.
So thank you, sir, for this 10 days. Actually, my work is not purely magnetism. So I work on ferroelectrics as well. So some of the concepts were not clear to me, and it would have taken me years to grasp the concepts. And through this course, I have learned a lot. And I think your knowledge in this area, it reflects from the very simple analogies that you can give. So I have gained a lot from this course, and I think it will be useful for my research as well, whatever I got from this course, be it from the lectures or from the tutorials. I think I can put to use. So this course has been very grateful, has been very helpful, and I'm grateful to have joined this course. And also I can also, next time if some such course is there, I can recommend for my peers also to join. Thank you.
Thank you, Nafisa, for your words. Okay, so any other participants? Are they interested to say something? Okay, if not, then.
Girls seems to be more sharing. Boys somehow are very discreet, huh? Spin polarized. See, there is a polarization already here. So, any of the boys would like to speak of something?
Okay, one of the.
Hi, myself Kulbhushan, and I works on fundamental aspects of magnetism. And for me, till now, the Spintronics was like, for me, like Spintronics was like some half metallic systems which I have studied, and the great like a larger value of resistance in some multi layers. I didn't know how these phenomena work in this in a device kind of systems, and I learned a lot here. And one thing which was really interesting is how sir presents these ideas in very simple terms. That was really nice, and I come up with new ideas in the field and want to explore more here. So thank you so much, sir.
Thank you, Kulbhushan, for your words. And so, any other participants? Okay, if not, then we'll. Okay, yeah, one more participant there.
Thank you, sir. Thank you, Prem sir, Tanmay Dutta sir, for giving us the opportunity to learn about Spintronics. My name is Rimli Sekia. I'm currently working in INUP projects in Center for Nanotechnology. So I took this opportunity to learn about Spintronics. So before coming to the course, I searched the YouTube for some knowledge about Spintronics, but I didn't find any good material on the topic, since it's a new topic, and the application part, I don't think it is quite available in YouTube and other materials. So I don't mind, but I have done the susceptibility and temperature plot wrong. All the two questions I had marked wrong in yesterday's exam also. So I have confusion in my basics, but I can say that I have learned from sir the application part. I have learned quite well. I have grasped it, but I'll try to relearn my basic once again. So thank you so much, sir.
So the YouTube recording is available. I mean, the recordings are available in YouTube, so you can always watch and learn.
Okay, thank you. Okay, any other participants? Okay, if not, then we'll proceed with the certificate distributions. So I would like to
someone also can say about the organization, right? So Datta, the students and the CET team, maybe Pallav.
Yes, I'm Pallavi. I am here on a short-term project under INUP. Thing is, I have been interacting with this group almost close to 6 months now, and it's really a wonderful team, and I'm really feel very happy and lucky to be part of this group, even for this short duration. and I know how much effort they have put, at least glimpses of it. I'm not directly involved in arranging all these things, but from my perspective, they have put a lot of effort to organize all these things, and I say it's a great success in terms of organizing the events and making facility easy for people who have come from all over the country and all. So my heartfelt thanks and gratitude to Tanmay Dutta sir and all my lab mates and friends, Atul, Shubhankar, Devdulal, Valyur and Shivender and Sriram, to everyone. Thanks a lot to you, sir. And one last thing about the course. I mean, two important things I would like to stress upon is the breadth and the coverage of the topic, list of topics. That was very great. So many major topics covered in 10 days. Second aspect is the way those things were covered and explained. There are many competent researchers in the field, but very few are skilled in rendering a topic. Teaching is a different art and talent, and Prem sir is very skilled and very talented in teaching. So thanks a lot to Prem sir, and thanks a lot to Tanmay Dutta sir for bringing him here and making this course possible. Thanks a lot.
Okay, so taking all these good feedbacks and supportive feedbacks from the participants, I would like to proceed with the certificate distribution ceremony, and I would like to invite Professor Harshal bin Amade sir to kindly come forward and distribute the certificates. So I will be calling the name of the participants, and they can come and they can receive the certificates. Astha Tiwari, Nilot Paldeka, B.N. Pallavi, Amlan Misra, Muhammad Ayan Anwar, Hodam Karanjit Singh, Sipra Aswal, Chaitanya Yadav, Subhajit Das, Suprabha Mandal, Kaustubh Bhavne, Nafisa Bingson, Rimli Sekia, Sanskriti Chanda, Kulbhushan Misra, thank you, Namade sir, for your valuable presence. Now I would request Professor Prem sir to further proceed with the certificate distribution of the participants. Ritik Roshan, Vigit KB, Athira P, Bodhisattva Dalai, Shivendra Pratap Singh, Priyanka Sharma, Naveen Kumar KR, and Guru Prasad Panda. Okay, left. Okay, we can. Okay, we'll do it later. Okay, we'll do it later. So before going to the final closing sessions of this tutorial or this course, I would like to give my personal feedback to Prem sir and Tanmay sir that my background is electronics and my master's is completely on the optoelectronics. So in my PhD, I have choose to work on the Spintronics since I found this field like interesting. But when I started my PhD journey in 2022, I struggled a lot with the very basic terms also to find. Okay, neither I can find some in very simple way the way the professor Prem sir has taught us. I have never find anything in very simple terms in any books or in the YouTube videos. So me and my colleagues like Subhankar Dojo started PhD with me in the Spintronics field. We have struggled a lot. So now we come to know the value of this course after the struggling of 2 to 3 years to find even the very basic things or the concept of Spintronics that can be explained in a very simple way that were done by the Professor Prem sir. Thank you sir for this, and I would like to say one more word that we'll have a future interactions with you sir, and if you have me and any participants will have any doubt or anything to discuss with you, we'll approach you. Thank you so much, and I would like to thank Dr. Tanmay Dutta sir also for organizing this course, and Professor Harshal bin Amades sir to present here for this closing ceremony of this course. So thank you everyone, and to officially close these sessions, I would request Dr. Tanmay Dutta sir to come on the stage for the closing remarks of this GIAN course that entitled as Spintronics Memory, Physics and Technology. Thank you.
You wanted to say something? Yeah. Good afternoon again. I was standing here, I think, how many, 10 days back? 9-10 days back, we were all here, right? So we began a journey, and today we kind of, let's say, I would not like to say end the journey, but let's say we kind of put a pause to this journey. I think our learning journey will still continue, but this is a phase of that learning process which you undertook here. And I really hope and I believe actually that all of you have learned a lot in the last 10 days. And I am pretty sure that you, when you return to your individual institutions, you would be returning with way more knowledge and experience about the basics of this field as well as the technology in this domain, right? So I have not been able to follow all the lectures, but I have been trying to follow online and offline his lectures through YouTube or sometimes here. And I have seen some of the instances how he has put across the concepts, right? So for example, I think one day I saw that he was teaching this STT, spin transfer torque, right? And right before that he was teaching spin polarization, right? So generally spin polarization would be covered by someone as like a very basic thing way before they reach to something like STT. But he put these two concepts together, and I asked him actually that day that you put spin polarization and then next to it you put STT, and then when he said that, I just wanted to carry forward from spin polarization to STT because it makes more sense, right? And I also thought about it, actually it is, right? So it's not about the content. I mean, as you said, there are micro contents available, there are contents available. I mean, not so much, but they're still there. But the way a teacher organizes it and then delivers it, I think is very critical. So this is one instance how he thought to deliver in his own way, and I think it's true that that helps if you follow this topic, spin polarization with STT, right? Similarly, I think one day he got this what is it called? Fidget, right? So he got that fidget. Again, I asked him, what are you going to do with that fidget? So what did he do with that fidget? Angular momentum, right? Spin and angular momentum. So he brings he delivers these things in his own way, and I have always seen him. I mean, as he said, we have known each other for like 10 years since I began my PhD. And I have always found him to be very good at this of explaining concepts, very difficult concepts. And Spintronics, of course, is not a very easy the concepts are not very easy, and there are very few who can actually deliver it with such ease. So I really admire that capability. I told the same thing, I think, in the beginning, and I think now all of you would be able to relate to what I said on the inaugural day, right? So thank you again, Professor Prem, for agreeing to come here. It has been very hectic for you, I know that. I know how our dates have changed, shifted, schedules have changed, and so many things. Like I think last, if I'm not wrong, we have been discussing the dates since last November, correct? Since last November, we have been trying to freeze on the dates again and again, and then so many things have come up. But nevertheless, he has made exactly 10 days to come here and deliver it. The ideal situation would have been him coming here for 14 days, rather 13-14 days. But again, he had something to attend just before he flew here, and he has something to attend again on Monday morning in Singapore. So it's very nice of him to really make time for us and deliver this. I'm really thankful for that. I am very thankful to all the participants here. I think the online people are not here with us today, right? They're not joining. Okay. But I would like to thank the online participants as well as offline participants here. You have been very actively participating. I know that the first day, the 2-3 UCLAP slides did not have 100% response. But I think from then on, from the first 2-3 questions, we have been seeing 100% and instantaneous response. So all of you got familiar with that, and you very actively participated, right? Also, I think your interactions, yesterday we had the poster session, so I heard, there was interaction with all of you, with me, as well as Prem sir also interacted with you. And we could see, there's a vast change in the way you are already dealing with the concepts. Some of you expressed concerns that how do we present a poster, because we don't work in this area, right? And some of you presented with very basic things that you have learned in this area. And that's also amazing, wonderful, right? I hope you all had a great stay here. You will all cherish these moments in your career going ahead, and I also hope that all of you will be able to pursue careers in this domain, be it at the master's, PhD or postdoc levels, and you will all benefit from this in the long run. Okay, so I would ask everyone to join me in applauding your efforts for the last 10 days. Okay, so a loud applause to all of you. So I would also like to thank Professor Nemade here and our Dean Administration, who is not here today. He could not join us, unfortunately. And the entire administration at IIT Guwahati, the CET team, they have been working in shifts, and they have been really being on the top of their work, relentlessly trying to make everything work smoothly without any hiccups. Right. Specifically, I would like to mention that I have seen many online, lectures being recorded, and I was following these lectures on YouTube. So I don't know if you have seen it. If you have not, just go back and see. You will see that the team from the control room is so adept at this that every time he is speaking, they will pan out, and he's showing something. They will pan out, and you will have an entire view. And when needed, they are actually panning only on the screen, right? Only on the screen. The screen is shared, and again there are when there is student interactions, there is this camera is being switched on, right? So all the multiple cameras and the screen share, everything is synchronized with the way he is delivering the lecture. So that's like hats off to the CET team. They have been doing a marvelous job at
IPL broadcast.
exactly, it's like a IPL broadcast. We just don't have that robot dog here, but it's like a IPL broadcast. Amazing. I mean, good job, I mean, by the CET team. So thank you to the entire CET team, right? And finally, coming to the TAs, volunteers, they have had, I think someone said I have had sleepless nights. I actually did not have sleepless nights. I think Professor Nemade said I still had some sleep. I would say the team organizing this, the TAs actually had sleepless nights, right? None of us would have organized this without their relentless work prior to this, and also during the duration of this program, right? So at 12 a.m. also we are receiving emails from them. Professor Prem and me are receiving emails from them at 12 a.m. about different things, right? So they have been working day in, day out, and they have managed all of this in spite of their own research that they are continuing. So none of them have stopped their research, right? I mean, they are all PhD students. They have not stopped their research. They're continuing the research. On the side, they are also helping with this course, and they have not only helped, they have actually pulled this entire course through on their shoulders, right? So a round of applause for all of you. Really great job, right? Thank you to all of you. You have done a great job, right? So so with this, I think I would like to thank everyone who has been a part of this program, and look forward to seeing you, meeting you, interacting with you in different roles somewhere, right? And Professor Prem will probably be visiting us, not probably, definitely visiting us in another few months, right? And let's see, we are also thinking of organizing a symposium then. If we can, we will again extend the invite to all of you to come join in the symposium, right? So with this, I would like to conclude this session. Yeah, thank you so much. We will have lunch served after this, but probably with a delay of another 5-10 minutes. Please bear with us. I know you're hungry, right? Your hunger for knowledge is, I think, partially quenched, but the hunger for food, I think, still remains. So join us for lunch, and have a safe trip back home for those who are going back, and all the best for your careers ahead. Thank you so much.
Thank you, Tanmay sir, for your words and sharing your thoughts. So before going for lunch, I would request for a group photo for all the participants. So please come on the stage and we can take a group photo together. Thank you. Yeah, and yeah, bring your certificates. Yeah.
What do you want to do? Please come stand here. I mean, it will take some time to arrange ourselves. Yeah, some of you please come in the back. You can make 2 rows. Don't worry, your certificates you can hold like this. Placard. Chairs. Let us move the chair. Just push it. So we'll wait. We need to wait, huh? The speaker is not here. You will check the frame, everything is there. लास्ट में स्टार एंट्री
So one thing I forgot to mention about the tutorials, it was really great, especially including pneumatics.
thanks
yes.
to Devdulal.
Yes, and Devdulal is a good teacher.
Devdulal, you can see your future now. Trial photos, don't worry. So sir wanted a photo like this, huh? Better than a photo like this. Thank you everyone. Thank you.